First of all, do these machines think like human beings? My answer is no, and I'll explain shortly why I feel this way. Second, the question of whether they can be considered more intelligent than humans is far more complex than it seems. Intelligence itself is a concept that needs careful definition. If you were to ask me, are these machines capable of playing chess better than any human possibly could? My answer would be yes, certainly. They can exceed human ability in chess. At present, many of these machines are already stronger chess players than the majority of humans. One important thing to keep in mind, by the way, is that when we build machines, our goal is often to create a machine that surpasses anyone, not just ourselves. If we happen upon a machine that can play chess better than we can, it might not impress us very much. We keep repeating this principle. But the real challenge emerges when these machines face the true masters. We tend to imagine ourselves as equivalent to these masters, and naturally, a machine must surpass the best human in every aspect that defines mastery. That is an incredibly difficult standard for any machine to meet. Now, regarding the question of whether we can make machines think like humans, my perspective comes from a fundamental idea. We aim to make machines work as efficiently as possible with the materials and resources we have. The materials at our disposal are fundamentally different from biological nerves and the processes of the human brain. Consider, for instance, the task of building something that can move swiftly across the ground. If we want to mimic nature, we might observe a cheetah running at top speed and attempt to create a machine that moves like a cheetah. Yet, in practice, it's far simpler to construct a machine that rolls on wheels or hovers slightly above the ground. Similarly, when we want to make something fly, we look at birds, but airplanes do not fly like birds. They achieve flight, yes, but the method is entirely different. Birds flap their wings, airplanes have propellers, jet engines, or internal rotating fans, often powered by fuel, which fundamentally changes how they move through the air. Thus, it's clear that machines will not think or operate exactly as humans do, and this extends to the realm of intelligence as well. Machines will not perform arithmetic in the same manner as humans, yet they can execute it more efficiently and accurately. Take basic arithmetic, for example. A computer can handle large sequences of numbers far faster and with fewer errors than a human can, though the final outcomes, the numbers themselves, remain equivalent. Attempting to make a machine perform arithmetic in the slow, cumbersome, error-prone manner of humans would be counterproductive. Humans are inefficient calculators. Machines excel because they streamline the process. To illustrate this, consider a simple experiment. I could present a human with a list of numbers and ask them to return every other number in reverse order. Even for a short sequence, say 20 or 30 numbers, this is challenging. Now imagine asking your computer to do the same with 50,000 numbers. It can handle it effortlessly, compute sums, apply various transformations, and store the data without forgetting. This demonstrates a crucial point. Computers outperform humans in specific, well-defined tasks. Yet humans consistently seek tasks where they can outperform machines, and they have many areas of superiority. For instance, think about pattern recognition. Imagine a person walking down the street. You notice a peculiar wiggle in their gait, the way their hair flips in the sunlight. From afar, these small details are barely noticeable, but a human observer instantly recognizes the individual. Machines, however, struggle to replicate this ability. Pattern recognition is incredibly difficult to codify into a definitive algorithmic procedure. You might try to teach a machine to recognize someone by inputting thousands of images from different angles, lighting, and distances. But even with high-resolution images and massive computational resources, machines cannot reliably account for every variable. The tilt of the head, slight movements, lighting changes, or minor obstructions all complicate the task. This is why certain tasks, like recognizing a familiar face or identifying subtle patterns, remain uniquely human. Consider a fingerprint analyst in a government office. This person compares prints carefully to determine matches. You might think it's a simple task. Line up the ridges, compare the dots. But the reality is far more complex. Fingerprints can be smudged, fingers dirty, pressure applied unevenly, or prints distorted by the angle at which they were taken. Some fingers have warts, scars, or other anomalies. These minor variations make it extremely difficult for a machine to perform the task quickly and reliably. Humans, on the other hand, can instantly recognize patterns and nuances. Their ability to generalize from experience remains unmatched. And it's not just recognition. Consider creative or heuristic problem solving. Can machines independently discover new ideas or relationships? Well, that depends on what we mean by independently. Computers can follow rigid, well defined procedures to prove mathematical theorems or explore geometric problems. They can execute complex algorithms to discover results we might call new. But they lack the broader intuitive sense humans use, an ability to apply analogies, consider extreme cases, or extrapolate insights from incomplete data. Humans can look at a problem and see a solution pathway without exploring every possibility. Machines require guidance or heuristics, otherwise, their problem solving becomes inefficient. A fascinating example comes from a machine designed by a researcher named Dr. Samuel Linnet. He constructed a machine, a computerized filing system that could explore complex decision spaces, such as a simulated naval game. In this game, players design a fleet of ships constrained by budget, armor, weapons, and rules about resistance to attacks. The machine's task was to optimize its fleet composition to outperform a hypothetical opponent. It didn't try every combination exhaustively, that would be impractical. Instead, it applied heuristics, prioritizing certain moves, testing extreme cases, and learning from results. Over time, it became extremely effective. One year, it designed a massive battleship, optimized to dominate the game. The next year, it adapted to rule changes by designing swarms of smaller, faster vessels. This illustrates a crucial point about machine intelligence. While the machine doesn't think like a human, it can learn, adapt, and optimize using feedback. Its intelligence emerges not from human-like thought, but from iterative improvement guided by heuristics. Moreover, the machine discovers clever, sometimes counterintuitive strategies that humans might overlook. Continuing with the theme of machine intelligence, let's explore the nature of heuristics in problem solving. Machines, as Dr. Linnet demonstrated, rely heavily on these heuristic strategies. In essence, a heuristic is a rule of thumb that guides the machine toward likely solutions without exhaustively evaluating every possible option. This is crucial because some problem spaces like chess, naval fleet design, or other combinatorial games are simply too vast for brute force search. A machine can be programmed to prioritize certain moves, avoid unlikely paths, and exploit patterns it has learned are often successful. In doing so, the machine exhibits behavior that appears intelligent, but it is not the same as human intuition. For example, in Dr. Linnet's naval game, the first year the machine created a single massive battleship, heavily armored and packed with firepower. While a human designer might have considered such an approach impractical, the machine calculated its effectiveness within the constraints of the rules and budget and found it superior. The next year, the rules were changed to prevent a single battleship from dominating. The machine adapted again, producing an enormous number of small, lightly armed vessels that could collectively achieve victory. What is striking here is not that the machine understood the game in a human sense, but that it could systematically explore possibilities, learn which strategies were effective, and adapt dynamically. This brings us to a critical distinction. Machine intelligence differs fundamentally from human intelligence. Humans can generalize, recognize patterns with partial information, and make leaps of insight that machines cannot yet replicate reliably. Machines excel in areas where rules are explicit, data is abundant, and operations can be performed repetitively at high speed without error. For instance, consider arithmetic operations, sorting or storing and retrieving large quantities of information. Computers can handle thousands or millions of numbers simultaneously, performing complex transformations and calculations instantaneously, tasks that would overwhelm human cognition. Yet, humans retain supremacy in tasks requiring pattern recognition, abstraction, and subtle contextual understanding. Take, for instance, the challenge of recognizing faces in varied conditions. We can instantly identify a friend across a crowded street despite changes in lighting, angle, hairstyle, or clothing. Machines struggle with this even when supplied with massive databases of images. Variations in scale, rotation, or environmental factors introduce complexity that makes perfect algorithmic recognition nearly impossible with current methods. Similarly, identifying a friend's unique walking pattern, subtle gestures, or characteristic habits involves nuances that humans process effortlessly, but machines cannot. Another fascinating illustration lies in fingerprint analysis. A human analyst can compare two prints and account for distortions, smudges, and differences in pressure. Machines, by contrast, require highly detailed rules and still struggle when deviations occur. Even small variations, such as a wart on a fingertip or an angle shift, can confound automated matching systems. Humans, with their capacity for recognition and judgment honed over years of experience, navigate these complexities seamlessly. The combination of intuition, pattern recognition, and adaptability remains difficult, if not impossible, to fully codify into a machine algorithm. This interplay between human strengths and hacking capabilities raises important questions about how we define intelligence. If intelligence is the ability to process information efficiently, solve problems, and optimize outcomes, then machines surpass humans in specific, well defined domains. If intelligence encompasses creativity, adaptability, and the capacity for abstraction, humans still lead. The remarkable thing is that humans instinctively seek tasks where they can outperform machines, carving niches where their strengths, pattern recognition, generalization, and ingenuity remain unmatched. Let us also consider predictive modeling, such as weather forecasting. Humans predict the weather by analyzing past patterns, applying physical laws governing fluid dynamics and atmospheric motion, and integrating their knowledge into models. The process is labor intensive, constrained by the sheer volume of data and computational limitations. Machines, however, can process massive data sets, incorporating historical trends, real time observations, and complex equations simultaneously. As a result, computers can produce faster, more accurate, and more detailed forecasts than human meteorologists alone. Here again, the machine does not understand the weather. It follows algorithms to identify patterns and extrapolate outcomes. Nevertheless, the results are often superior to what humans can achieve unaided. This leads to another critical consideration. What happens when machines are not given explicit procedures, but instead are allowed to develop solutions using heuristics, analogies, or trial and error approaches? Here, the line between apparent intelligence and mechanistic computation blurs. Dr. Linnett's machine, for example, was designed to explore multiple solutions, guided by heuristics that favored moves near the center of the board, or extreme scenarios that humans might not consider. Over time, the machine learned which heuristics were most effective and prioritized them in subsequent iterations. It learned without understanding in the human sense. But its adaptive behavior produced results that mimicked intelligent decision making. The evolution of heuristics also introduces the notion of feedback driven learning. In the naval game example, when the machine identified a particularly effective heuristic, say, the strategy that produced the massive battleship, it assigned credit to that heuristic and increased its usage. Over time, effective heuristics dominated, while less useful strategies were de emphasized. This self reinforcing learning process mirrors some aspects of human cognitive development, where successful strategies are reinforced through experience and less effective approaches are abandoned. Yet, even as machines demonstrate adaptive learning, they remain bound by the frameworks and constraints imposed by their programmers. They do not experience curiosity, intuition, or the aesthetic appreciation that humans attach to problem solving. For instance, a human might invent a clever or elegant solution purely for aesthetic satisfaction or creative delight. Machines, by contrast, optimize for efficiency, effectiveness, and rule compliance. Any appearance of creativity is a byproduct of algorithmic exploration rather than conscious insight. This distinction becomes more pronounced when examining abstract problem solving. Humans often discover new principles by analogy, lateral thinking, or imaginative projection. Machines, unless explicitly programmed to consider analogies or extreme cases, lack the ability to make these leaps. They explore solutions within defined parameters and rely on heuristics to guide their search. While the results may appear intelligent, they are fundamental, lie algorithmic, lacking the flexible, context sensitive reasoning that characterizes human thought. In chess, for instance, machines have surpassed humans in raw capability. They can calculate millions of moves in a fraction of a second, evaluate positions with extraordinary precision, and identify optimal strategies beyond human comprehension. Yet, even here, humans provide an important complement: strategic understanding, pattern recognition, and intuitive judgment. Machines excel in calculation, Humans excel in insight. The combination of human and machine strengths, collaborative intelligence, can produce results neither could achieve alone. Another area where machine efficiency is unmatched is memory. Humans are limited in their capacity to retain and recall large data sets accurately, while machines can store and retrieve vast amounts of information instantly. This advantage underpins their superiority in tasks like complex simulations, database analysis, and combinatorial optimization. At the same time, humans are capable of selective attention and prioritization, intuitively focusing on the most relevant information for a given task, something machines often struggle with unless explicitly guided. Returning to the notion of recognition, consider how humans perceive novelty and variation. A human walking down a street immediately identifies a familiar face despite changes in clothing, lighting, or context. A computer, however, must account for each variable explicitly, making recognition a laborious and often imperfect process. Similarly, tasks requiring qualitative judgment, such as evaluating a creative work, appreciating a subtle nuance, or detecting a social cue, remain largely inaccessible to machines. These abilities are grounded in experience, intuition, and a rich understanding of context that is difficult to formalize algorithmically. The interplay between end machine efficiency and human adaptability raises profound questions about the future of intelligence. Machines will increasingly surpass humans in computational speed, precision, and data handling. They will solve problems too complex or voluminous for humans to tackle alone. Yet humans retain irreplaceable advantages: pattern recognition, creative insight, intuitive reasoning, and adaptability. Intelligence, therefore, is not a single dimension, but a spectrum, with humans and machines excelling in different domains. Ultimately, what does this mean for our relationship with intelligent machines? It suggests a paradigm of collaboration rather than competition. Machines can augment human capability, handling repetitive, data intensive, or computation heavy tasks. Humans provide guidance, interpretation, creativity, and judgment. Together, the combination of human intuition and machine precision can achieve outcomes neither could accomplish independently. In conclusion, machines will never truly think like humans. They lack intuition, self awareness, and conscious insight. They do not experience curiosity, emotion, or aesthetic appreciation. Yet, within their design parameters, they can exhibit remarkable intelligence, adaptive problem solving, heuristic learning, and unparalleled computational efficiency. Humans, meanwhile, retain unique strengths in recognition, abstraction, and creativity. The future of intelligence lies not in choosing one over the other, but in understanding how humans and machines complement each other, each bringing its strengths to bear on problems that neither could solve alone. By exploring examples from chess, naval strategy simulations, pattern recognition, arithmetic, and predictive modeling, we gain a nuanced understanding of intelligence. Machines are powerful, fast, and reliable, excelling in structured, well defined domains. Humans are flexible, creative, and context sensitive, excelling in ambiguity, intuition, and novel problem solving. Together, they form a hybrid intelligence, a synthesis that promises to reshape the boundaries of knowledge, computation, and discovery.